working? Yeah, it's working. Okay, so this question comes from JEE, this year JEE, and this question number 12. Now, this comes from probably lab. They're trying to test if you had a lab and you use some lab formulas. So this is about uncertainty. So here is a diffraction grating formula. So a single slit width is B, and it's performed slit width using this equation. B is the slit width, and D is the distance, like this. Let's put the arrangement. So here is the screen. This is capital D. This is B. Let me erase this here because it's a single slit. This whole distance, distance from here all the way here is D, and so this is the center O, and so there will be this is not completely right. So this is diffraction pattern I'm trying to draw. So let's redraw it. So the central one is like that. Central one is like that, and then the next one is like that, and next one there's this m equals to 3, m equals to 2, m equals to 1, and this m equal to 0. This is the central maximum, and this is going to be twice as wide as the other guys. Okay, so this is the diffraction, and from the center to over here, distance D. In this formula later on, it's gonna tell us that m is 3. Okay, so you really don't need to know any of these to actually solve this problem. Just you need to know the formula connecting them is this. The formula connecting them would be B times small d over capital D equals to m lambda. So these are kind of exact values, but these are experimental values, and so we need to deduce this guy. So we've known D is a plus minus delta D, and capital D is plus minus capital D. That's how it's been measured. So the question is, well, using this information, can you deduce B plus minus delta B? So the question is, what is this delta B? Okay. So general approach to this kind of multivariate problem is take a function of x and y. So two variables. These are the two independent variables, and this is the dependent variable. So in our case, will be B will be function of D and D. So in this case, if you want to have it's differential, so you'll have a d partial derivative with a little d delta D. So this will be like delta. Otherwise, you'll have a little d look weird. Delta d, okay. So we have a b, and so here is going to be partial of b with partial of d, delta d, partial b with partial of d, delta d. Now it turns out this is mathematically precise, but these guys can turn out to be positive or negative, but you want this to capture errors in both, not subtract one error from the other. Then you have a couple of ways of doing this. So if I so in actually wrong but often used, but used in JEE syllabus. This is not how we do it. It doesn't have any. It's just it's a so-called simple-minded formula. So you take absolute of this, absolute, so try to kill the negative sign of that. So delta f dt delta, oh, this will be dx dy. You can have as many variables you want. So x, make an absolute of that plus df dy delta y, absolute that, and say this is the absolute of f. So that turns out does not have any theoretical justification. But so these are we're going to use for this problem, okay? And below I'm going to show you what's a more theoretically justifiable way of doing it, but don't do that for this test, okay? This kind of test is just use this formula. So let's just complete this, and then if you're interested, you can actually look at the last bit. So when I do this, it's going to be delta b will be absolute value. So the b is going to be m lambda d over d from that PD, that formula above, okay? From this formula. So these are formulas, so it's gonna feed into that. So thinking of this as a function of this guy and this guy. So let's see, we do this guy first, minus m lambda d over d square delta d. So remember I was telling you there's a minus sign income. We want to kill the sign because we want to have the largest error, because errors should add. That's the justification for this. This is not correct justification, but that's the justification, okay? We should add, and then it's going to be m lambda over d delta d, because the derivative will be just 1. This derivative, that delta d, okay? So that's the answer, and just put numbers and get the answer. But actually, turns out you can do a little better in terms of calculation and preventing error from happening by dividing everything by b, by this formula, dividing everything by b, dividing b, and so this will turn out to be, it will kill m and lambda and d and 1d. So it's going to be minus delta d over d. Let's get rid of this minus because I'm doing absolute value. And this is going to be delta d over big D. And so we calculate this and then multiply by b. So we need to figure out delta b. So it's going to be times this quantity. B will still have to be calculated, m lambda d over d. Okay, you have to still calculate this thing. And then, okay, so let's put the numerical value they gave us. So they gave us that m is 3, little d is this, and capital D is this, and lambda is 600. Okay, so these are, using these I can find, better be careful units. So B will be m lambda capital D over D. So we can just, so m is 3, and we're supposed to get B in delta B in micrometers. So we can just convert this in micrometers. But initially you just write down everything in terms of meters. So you have a 600 times 10 to the power minus 9 meter. And then we put underscore for unit, so I don't confuse with the letter M, which is this. This guy is M. And D is going to be, capital D is 1 meter, so 1 meter. Little d is going to be millimeter, 5 millimeters, so 5 times 10 to the power minus 3 meter. So meter cancel, and this guy cancel makes it 6. So this is a micrometer. So just, we have to deal with just this, and we can just, and so this becomes 360 micrometers for the B. So we need from this we need delta D and delta D also. So it says that D and little d are measured with a scale of least count 1 centimeter. So least count is considered to be a good indicator of the error. Okay, so this is 1 centimeter, and this is 1 millimeter. So the unit's actually going to play a role. All right, let me copy down here. So 360. So this is 360 micrometer, and delta D was 1 millimeter over 5 millimeter. That's easy. And this is 1 centimeter over 1 meter. We can make it 100 centimeter. We could just drop the absolute sign, right? So this is 360 times 0.2 plus 0.01 micrometer. So I'm just going to multiply 360 with 0.21 micrometer. So get rid of this, and this is that way, decimal is here. So that will be 36. And then 2, right? So I don't, earlier got a different answer, so I don't know why I'm getting this answer. So let's see, 36 and 21, right? It's 2.1, so we have a 36. Oh, this is 2. That's why we're getting this answer. Is so, and decimal comes out over here. So this is 75.6, which will round to 76 micrometer. So that will be the answer. But we already said that this is a simplified formula, and in that answer is correct for this test. Now let's take a moment to talk a little bit about. So I have this formula. Rather than do it this way, combine the errors here and errors here using absolute value, we assume that this error is independent of this error, okay, and they are normally distributed, meaning they're distributed according to some Gaussian. When you make those assumptions, then if you just look at the fractional error, okay, we're just going to look at the fractional error. So divide by f all through, just like we did divide by b all through. Let's look at that quantity. So we are going to have 1 over f df dx delta x plus 1 over f df dy delta y, and we are assuming this error and this error are distributed in a Gaussian way. So if you were to like a delta, if you look at this, let's call it delta f to do with x, and this delta f, let me simplify even further, okay. Okay, just let's not divide. I was thinking to make it parallel to that, let's just call this guy like that. All right, so it's easy to look at, you can get the idea. So if you look at delta x, and you can say this when delta x is going to be some plus and minus, and so it's so if you look at delta x, it's this thing is a Gaussian, this is Gaussian, and this is Gaussian, okay. So if this is Gaussian, they're independent. If you assume that, then work through the if you work through the probability distribution and how the errors will propagate, then you'll find that delta f will be the error here, square of the error here, which will be like a sigma square or standard deviation square. The variance in this will combine the square of variance of this and variance of this. So delta fx this quantity square delta f y quantity square. And if you're going to do the fractional, then you just have to do delta f square, just multiply by f square, everybody. So delta fx over f square plus delta fy. So this has to do with the variance in the distribution. And so if you work this out in our problem, you're going to get delta b over b square will be delta d over d square and delta d over d square. So it's going to be sum of the squares instead of sum of the absolute values. And when this leads to delta b is b square root of this stuff, and this turns out to be, I think I worked out the formula. You can just play around and find if this is actually turns out to be 72 micrometer. So in a way, it's a more justifiable because you're modeling the data and the error as a kind of probabilistic distribution, statistical distribution. And so there's a theory behind it. And using more solid theory behind it, you'll get this. And this is how it is done in the lab, more advanced lab, not just kind of really intro labs. So this way of doing is called so-called aiding in quadrature. Okay, so that's the name of this. So the error side in the quadrature, don't write an absolute, but for the test, don't make it that complicated. For the test, do the absolute, okay? Okay, with that said, I think I'm done with this video, and I'll just try to hassle a little bit that you can subscribe to this channel, so it's that a lot more people know about that, and hit the like button if you like this kind of explanation, a little more detailed discussion of the same questions you might find online discussed very briefly. If you have a question, maybe I'd like to hear about that. You can check out my website also. All right. With that said, I'll see you in another video. Okay, bye.